Session on advanced statistics. This is an important section. You don't get a lot of hardcore statistics questions in your paper B exam, but nevertheless you do get questions that ask you to choose statistical tests and asks you to interpret the results of statistical tests. So it's important to understand the basic concepts in advanced statistics. So I'm going to take you through some of them now. So let's start with data types. When you collect data for any research study, the data can be basically of two types, one of two types. Either it could be qualitative data or quantitative data. Qualitative data is data that can be described, but it does not have any unit of measurement. You cannot really measure it just like how you measure a quantifiable parameter. So what are the different types of qualitative data we have? We have two types of qualitative data, nominal and ordinal. What is nominal? The term nominal tells you what it is. Nominal means only naming is possible. You can name it, but you cannot really measure it or attach a value to it or say one is higher than the other. Nominal data usually could be binary data or multiple categorical data. A good example of binary nominal data is gender, male and female. There are two genders. So you can describe them, you can give a name to them. You cannot really say one is bigger or larger or greater than the other. Could you say male is better than female or female is better than male? You better not. So you cannot say things like that. And that's the nature of nominal data. Can you give me an example of a multiple categorical data? Blood types. A, B, O, AB. So these are multiple categories. Ethnicity groups is also multiple categorical data. So nominal or categorical data could be binary or multiple categorical. What about ordinal data? The word ordinal, the term ordinal means there is an order. So examples of ordinal data includes things like cancer staging. Have you heard of TNM staging? Tumor node metastasis staging, T1, T2, T3. Pain rating between 0 and 10. You ask patients to rate their pain, or you ask patients to rate their mood between 0 and 10. Those kind of ratings are called ordinal ratings. Psychologists use the term Likert rating. So Likert or ordinal rating is also qualitative, descriptive. Now you might ask me, there is a number we attach to Likert rating 0 to 10. Would that not be quantitative? No, because this number is only descriptive. It only gives you an order. 0 is lower than 1, 1 is lower than 2, so on and so forth. It doesn't have any unit attached to it. So can you measure mood in kilograms? No, you can't. Okay, so there is no unit attached to it. So this is why it's called ordinal. Nominal and ordinal both are qualitative. Okay, nominal you cannot put in order. Ordinal you can put it in order. Next comes quantitative data. Now statisticians don't usually worry about qualitative data. They are not interested in qualitative data because you need quantitative data to do statistical analysis. So quantitative data is data that is countable or measurable. What kind of quantitative data we have? The major type of quantitative data is continuous data. Continuous data is any data that has a meaningful metric. So for example, there are two types of continuous data. Interval data and ratio data. Interval data. What is interval data? Any data that you get from using a rating scale. Any added up score of a rating scale is an interval score. So Hamilton depression scale, if you add all the individual items up, what you get is an interval scale. Remember, the individual items could be Likert items, they're ordinal, but when you add them all up, they become interval scale. Okay, what do we mean by interval scale? In an interval scale, interval is difference or gap. The gap between two scores are always meaningful. So if a patient scores 30 points and another patient scores 25 points, the difference between them is 5 points. You can use interval scales to see what is the change in score that happens over time when you treat somebody. So somebody has a score of 30 in Hamilton depression today. You treat them for depression. 1 week later, the score becomes 25. The difference makes sense. The difference tells you 5 units change happens with treatment. Okay. But ratio is not very meaningful when you use interval scales. For example, let's say you have two patients, one scoring 30 points on Hamilton depression, another scoring 15 points on Hamilton depression. You cannot say to your second patient that his or her depression is only half as intense as another person's depression. Can you ever make those kind of statements? your depression is double the time severe than other person's depression. No, those things do not make sense when you use interval scales. Okay, so when you use an interval scale, difference makes sense, but ratio doesn't. Okay. What about a ratio scale? Ratio scale is the most evolved form of quantitative data. Ratio scales, most biological measurements use ratio scales. In ratio scales, differences make meaningful value. Ratios also make meaningful values. So blood pressure. Okay, so your blood pressure today is 180 millimeters of mercury, and it drops to 90 millimeters of mercury after you take an antihypertensive. So your blood pressure halved after you took a tablet. So that kind of ratio phrases are meaningful. Ratio explanations are meaningful when it comes to ratio data. Okay, so you could say your weight is 50 kilogram, your son's weight is 25 kilogram, and your son is only half as heavy as you. So that statement makes meaningful sense. That's ratio data. Remember, almost everything that's biological is measured using ratio data. Kilogram, weight, height, age, BP, anything that's a biological metric, you can close your eyes and confidently say that's a ratio data. Okay, so that's how we classify data. How do we classify variable? When we collect something, it's called data. When we analyze it, we call it as variable. So there are two types of variable: independent variable and dependent variable. Independent variable is the variable that's controlled by the experimenter. Dependent variable depends on the value of the independent variable. Let's say if I want to study the effect of diet on somebody's weight, diet is the independent variable and weight is the dependent variable, because weight depends on diet. So once we collect data, you start analyzing data. You could use two types of statistics to do the analysis: descriptive or inferential. Descriptive statistics uses things like distribution curves, graphs. It only describes the nature of the data within a same sample that you collect the data from. It doesn't tell you anything about the population. So you cannot generalize from sample to population using descriptive statistics. The purpose of descriptive statistics is to help communicate, describe the measurement that you have taken. Okay, so let's say I'm collecting the age of everybody who's attending this webinar, and I want to tell someone else what is the age group of people who attend these webinars. And I can measure all of your ages and find a middle value, central tendency value, usually the average, and that will help me to communicate with another person. So that kind of statistics, the averages, mean, median, so on and so forth, those kind of statistics are usually descriptive statistics. Okay, inferential statistics is one step further. If I want to establish whether the people who attend this webinar, the age of the people who attend this webinar is comparable to, or is it representative of, the age of psychiatrists taking MRC psych exam, this diet, then what I can do, I can collect all of your ages, and then I can also get the information about the age of the people who are registered for the exam, and I can make a comparison. I can do a t-test. I can do some kind of significance test to compare if your group has a significantly different age distribution compared to the group that takes the MRC psych exam, this diet. So that kind of statistics where I am taking a hypothesis. My hypothesis is people who attend webinars are going to be, I don't know, slightly younger than people who are really taking the MRC psych exam. So if that hypothesis could be tested, if I want to test the hypothesis, I'm going to use inferential statistics. Okay, so I'm generalizing from a sample to the population. That's an important key element of inferential statistics. You take an observation from a sample, but you try to make an inference about the population. Okay, this is why it's called inferential. When you do inferential statistics, you will be choosing statistical tests to prove significance of your observation. You don't do the kind of significance testing for descriptive studies. So just make it easily memorable for you. Remember, whenever you do audits, you only do descriptive statistics. When you do research studies, you generally do inferential statistics. Okay. Right, let's talk about distribution of data. Now we're going to do descriptive statistics. We're going to describe how data is distributed. I collected all of your age values. There are so many of you today, let's say 100 of you today attending the webinar, and I want to collect the central tendency of all of your age. So what are the different ways in which I can do it? I can add all of your ages up and divide it by 100, and that will give me the arithmetic mean. That's called average, mean, that's the central value. I can also do median. Median is I can rank order everybody in this webinar from youngest person to the oldest person, and the middlemost person's age will give me the median. And if I have 100 people, the middlemost person is not the 50th one, not the 51st one. So let me take both 50th value and 51st value. I will average it, and that average will give you the median. Okay, so if I have 99 people, it's easy. 50th person will be the middlemost person. But if I have 100 people, even number, then I will take two middle values and average it. That'll give me median. Then I have mode. What is mode? Mode is the most commonly occurring value in a distribution. So if I have 12 of you, all of you belong to the age, all of you have the age value of, let's say, 29 or 31, let's say 29, let's keep you younger. And so that 29 will give me the mode value of this distribution. So all of these are central tendencies: mean, median, mode. Now, central tendency itself is not sufficient to convey information. If I want to tell someone, what is the composition of your group, I can say your mean age is 33, but that wouldn't tell the other person, that wouldn't convey any information about whether there are a lot of old people and a lot of young people in this group. Let's say if you have 20 people here who are age 20, and if I have 20 people who are age 50, then somehow the average might come close to 33 or 32, right? So the outliers, people who have high values of 20s or values of 50s, can influence and bring the average to look as if it is normal. Okay, I wouldn't know if this group is having a lot of young and a lot of old people, or is it having most of the people distributed around age 33. So if I want to convey that information, how is everybody distributed around the central value? What is the dispersion? What is the spread of everyone's value around the central value? Then I have to give you some measure of dispersion along with the measure of central tendency. So we usually use, the most easy measure to remember when it comes to dispersion is variance. Variance is nothing but take the mean value, subtract every individual's age from the mean value. So you will get a difference. Square the difference. Okay. So for every person, you have the difference from average and you square it, right? And you add all of those squares and divide it by total number of observations. That gives you variance. In other words, variance is the sum of the square of the differences from average. Okay, that's variance. Now the problem with variance is it has a unit that is square of the unit of the original data. So if age is collected in years, then variance will be measured in years square. What is the meaning of years square? Not very meaningful. So I'm going to take a square root of the entire variance, and when I take a square root of variance, I get standard deviation, SD. Okay, so SD is most commonly used alongside mean. Whenever people present mean of a data set, they also present SD, standard deviation. You can also measure dispersion using range. You can just tell people what is the lowest value, what is the highest value, and find the difference between the two. Okay, if the dispersion is very high, the range will be high. Let's say if you have one person here aged 20 and one person here aged 70, so the range of your group will be 50. That's a wide range compared to range of people between 30 and 40. So that will be 10. Okay, so range gives you a measure of dispersion. You can also do interquartile range. What is interquartile range? Now, to understand interquartile range, you got to understand median. Median is the centralmost person. Centralmost person in a group of 100 people is the 50th person. Okay, so median can be median can be called 50th percentile. Okay, the 50th percentile value is median value. So once I have the 50th percentile, I can split the group into lower half and upper half. And then for each half, I can take another median value. This median will be the 50th percentile of the each half. But for the whole population, for the whole sample, this median of each half will actually be the 25th quartile and the 75th quartile. Okay, so 50th centile is median. And if you take 50th centile, split the group into two, and take another 50th centile in each of these two split groups, you will get two quartiles. Okay, so that will be the 25th centile and 75th centile. So totally we have 4 quartiles. In a group of 100 people, you have 25, 25, 25, 25. 4 quartiles. Okay, and the range, interquartile range, IQR, is nothing but the difference between the 25th quartile value, 25th centile value, and 75th centile value. Okay, 25 and 75. The difference is interquartile range. The first and last value difference is range. The 25th and 75th value, the difference is interquartile range. Okay, what is SEM? I will tell you what SEM is later on. SEM is a special type of dispersion. It's called standard error of mean. So far we have seen several values of central tendency and several values of dispersion. A box whisker plot is a nice graphical method of putting all of these values in picture, in visualization. So a box whisker plot usually looks like this. It has a box, it has two whiskers on either side. You can keep it horizontal or you can keep it vertical as well, doesn't matter. So here you have all the interquartile range captured in the box. So this will be the 25th percentile, this will be the 75th percentile, and you will have the whole interquartile range captured in the box. Anything outside of the interquartile range will be shown in the whiskers. Usually this is lower extreme and this will be the upper extreme. So you can capture 95 percentile values between the two extremes. Okay, in other words, two standard deviation values. I'll tell you what these are as we go along when we see normal distribution. So you can capture those values between these two, 95 percentile here and 50 percentile of values here, between 25 and 75. Okay, so this is box whisker plot. Usually we show median by a continuous line. A mean can be shown using a dashed line. If you want to show the mean can also be shown using a dashed line. Okay, so now let's talk about the different types of distribution. So you have a set of data. I have measured age of 100 people in this webinar. I can then plot all the ages and see what is the distribution of ages like. So I can, the plot that I will have is called frequency plot. I just have age in one axis, let's say from 20 to 70, and then I count the number of people, frequency in each age category. How many people are 20, how many people are 21, 22, 23, so on and so forth. So if I have a nice smooth curve looking like this, okay, nice smooth bell-shaped curve, that means most people are in the middle. Most people have the age group somewhere between, I don't know, 33, 35. Some are 20 years old and some are 70 years old. And this will be a nice, smooth, normal distribution. If I sample enough, most biological data will fall under normal distribution. Okay, what do you mean by sample enough? The sample enough is the phrase that we use for central limit theorem. So if the sample is decent enough, around 30 people at least, if you capture for any biological measure, then that will give you a normal distribution. All continuous data, both interval and ratio data, will work with normal distribution. Okay, you cannot have normal distribution for qualitative data or frequency count. If you just count number of people in a group, that will not give you normal distribution. Okay, so a characteristic of normal distribution curve is smooth uniphasic curve. This is smooth curve, only one peak, so this is uniphasic, and the mean value will be same as the median, will be same as the mode for a normal distribution. So the central value here, the line I draw here, x bar is mean, and the mean will be same as median, same as mode. That's a special property of a normal distribution graph. The other thing you have to remember is whenever you have normal distribution, you can predict how many people will fall, what will be the frequency that falls between mean value and one standard deviation, mean value and two standard deviation, and mean value and three standard deviation. Between mean and one standard deviation is always 34%. Between mean and two standard deviation it is 34 plus 13.5, nearly 67.5. Okay, so between mean and three standard deviation, so you can keep adding these things. Sorry, 34 plus 13.5 is 47.5, and then you have 49.9. Okay, so you can keep adding these values and fixed numbers will fall. The three numbers I want you to remember though is the value between minus and plus 1 standard deviation is 68%. The value between minus 2 and plus 2 standard deviation is 97.5%. And minus 3 and plus 3 standard deviation is 99%. Okay, because this is a smooth curve, there is a mirror image. You can cut the curve into equal halves, and you will get these numbers. 68 split into 34 and 34. 95 split into 47.5 and 47.5. Okay, so 68, 95 and 99. Just remember those numbers. Okay. So now we have a normal distribution curve in the center, and I have two other different shapes of curves I've shown in the left side and the right side. What are they? These are called skewed distributions. So this is a positively skewed distribution because mode is in the center but mean is higher. Mean moves positive direction. Mean moves in the positive direction. That's called positive skew. When can you have a higher mean than median and mode? If you add a lot of outliers who have high value, then mean will move towards the positive direction. Okay, When will you have negative skew? If mean moves towards the negative direction. So if you add outliers who have really low value, outliers are not going to immediately change your median or mode. Mode is number of people with a specific value. That's not going to immediately change if you add few outliers with different values. Okay, but mean is very sensitive to outliers. Median is second sensitive, and mode becomes a little bit less. Mode is a little bit less sensitive. Okay. So the thing you have to remember here is mode is always on the shorter side. This is short side. This is long side. So mean goes where the tail goes. This is tail because this is long. So mean goes wherever the tail goes. Okay. So positive skew, right longer tail. Negative skew, left longer tail. Longer tail on the left side. Okay. So this is what skew is all about. Now, whenever the distribution is skewed, mean will not be same as median, will not be same as mode. Okay, so remember, mean same median as mode, mean is same as median and mode only in normal distribution. Okay, so now there are two types of inferential statistics, inferential tests that we use in clinical research. What are they? Parametric statistics and non-parametric statistical tests. Parametric statistics can be used whenever there is normal distribution. If you don't have normal distribution, you have to use non-parametric statistics. But you know, statisticians don't really like using non-parametric statistics. Parametric statistics are more robust. The only condition you have to satisfy for parametric statistics are the observations must be independent. It should follow normal distribution. Okay. And don't worry about the homogeneity assumptions. It's not important for your exams. So normal distribution is the most important assumption for you to apply parametric statistics. But non-parametric statistics is not preferred by statisticians because it's less robust. Even though it doesn't have any assumptions to satisfy, it is less robust. You cannot draw confidence limits with non-parametric statistics. It's not easy. Let's say it's not easy. You can do it if you do bootstrapping, but let me not go there. You can actually you cannot simply draw. It's not easy to do confidence intervals from non-parametric statistics. Okay, so this is a problem. This is one of the reasons why statisticians don't like non-parametric statistics. But if the data is skewed, you have to use non-parametric statistics. Okay, but you know what? Statisticians still try to well, let's say process the skewed data and make it work for normal distribution. That kind of processing where you change skewed data into normal distributed data is called transformation. So you can transform skewed data and then manipulate it using parametric manipulations. Okay, but in your exam, if they don't say anything about these processes of transformation, if they only give you skewed data and ask you to choose a statistical test, choose something that is non-parametric. Okay, let's do some questions now. Question 1. A study was conducted to investigate the associations of severity of OCD to incidence of depression. The following information was recorded. Sex, 0 female, 1 male. Age in years. Severity of OCD, 0 mild, 1 moderate, 2 severe. 4. Duration of symptoms in years. In the same order given above, choose the type of variables described for each observation. So this is about types of data collected. Nominal, ratio, ordinal ratio. Is sex nominal? Yes, it is. Is age ratio? Yes, it is. Severity of OCD, is it ordinal? Yes, it is. Duration of symptoms in years, is it ratio? Oh yes, it has a unit, so it is ratio. So the answer should be nominal, ratio, ordinal ratio. Choice 1. Okay, so nominal ratio, ordinal ratio. Which of the following is true in negative skew? Mean, mode, median are the same? No, that's true for normal distribution, not for negative skew. Mean is less than median? Yes, mean is less than median when it comes to negative skew. That is the correct answer. Mean is less than median. With respect to mean, median and mode of a normally distributed data, which of the following assumption is correct? Mean is greater than median. Mean is equal to median and mode. Yes, mean is equal to median and mode. That's correct for normal distribution. In a scale designed to measure creativity of a population, it was found that the scores obtained were normally distributed. If mean score is 10 and standard deviation is 1, then the variance will be 1, 100, square root of 10, 110, 0.1. So standard deviation is given as 1. How do you calculate variance? Square root of variance is standard deviation. So square of standard deviation will give you variance. 1 square is 1. So the answer will be simply 1. Answer is 1 here. Okay. So if you just square the value, standard deviation value, you will get variance. The answer is 1. In an attempt to detect the stability of the diagnosis of binge eating disorder, the median lifetime duration of binge eating disorder was found to be 10 years with interquartile range of 3 to 22. So you have median value 10 and interquartile range 3 to 22. Which of the following statements regarding the lifetime duration of binge eating disorder is correct? In 25% of patients, the lifetime duration is less than 22 years. In 75% of patients, the lifetime duration varies between 3 and 22. 75th percentile is 22 years. Is that correct? Yes. See, 3 is 25th percentile, 22 is 75th percentile. Okay, so between 3 and 22, how much percentage of patients will fall? 50%. So 25 is wrong. Sorry, 75% of patients lifetime duration varies between 3 and 22 is wrong. It's only 50%. Okay, 25% of patients lifetime duration is less than 22 is also wrong. 75% will have less than 22 because this is 75th percentile. 75th percentile value is 22 is correct. Okay, so the answer is C. 75th percentile value is 22 years. Which of the following is not a measure of dispersion? Range, variance, standard deviation, mean, standard error. So very straightforward question. Mean is not a measure of dispersion. Mean is a measure of central tendency. While plotting the distribution of a variable, it is noted that the data is skewed towards the side with higher positive values. So this is a positive skew. Which of the following will be true? Curve with no peaks will be obtained. Mean will be greater than the median. Yes, mean will be greater than the median. This is straightforward. Standard deviation is more often used than variance while discussing the measure of dispersion of data. This is because standard deviation can have both positive and negative values. Is that correct? No, standard deviation can only be positive. Why? You're taking squares of numbers and then you are taking a square root of it to get standard deviation. So it can only be a positive number. It can never be negative. Same for variance. Variance can never be negative. Okay. Standard deviation has no units. That's false. Standard deviation has the same units as the primary data. So C is correct. Standard deviation is expressed in the same units as the primary data. This is the reason why we prefer SD to variance. C. Nine. The number of days that a series of 5 patients had to wait before starting CBT at a center is as follows: 12, 12, 14, 16, 21. The median waiting time to get CBT is, so you have a series of numbers, they are ordered already, 12, 12, 14, 16, 21. What is the median? So the middlemost value is 14. Okay, so the median is 14 days. 14 days. 100 patients on clozapine had their blood pressure recorded soon after 1 dose of clozapine was given. The mean systolic BP was 150 millimeters of mercury. If the standard deviation was 10, calculate the standard error of the mean. So I told you I will tell you more about standard error of the mean. So here I'm going to say more about standard error of the mean. What is SEM, standard error of the mean? It's nothing but standard deviation divided by square root of the sample size. So if you have standard deviation value, divide SD by the square root of sample size. Okay, if you do that, what you get is called standard deviation, standard error of the mean. Okay, SD by square root of sample size will give you standard error of the mean. So in this question, standard error of the mean is requested, is what's required, and you have sample size is 100 and you have standard deviation is 10. So let's do this. 10 is the standard deviation, sample size is 100, so 10 by root 100, root 100 is 10, 10 by 10 is 1. So standard error of the mean here is 1. Remember, standard error of the mean will always be smaller than standard deviation. Why? Because you are deriving standard error of the mean by dividing standard deviation by another positive number. Sample size can never be less than 1. It's always a positive number. It's greater than 1. So when you divide one positive value by another positive value, the fraction will be always smaller. So standard error of the mean is smaller than SD. You can do a sanity check by quickly looking at your answer. 1. Is 1 smaller than 10? Yes, it is. Okay, so you should not choose 100 or 15 here. Okay, so 1 is the right answer, D. So far we have seen different types of data and how do we classify variables and what is the nature of parametric and non-parametric statistical tests. We've also seen what is descriptive statistics, and we have looked at measures of central tendency and dispersion. We talked about skew and normal distribution. We also talked about SEM, standard of the mean. So now we are moving to next topic, hypothesis and inferences. So the main reason, this is inferential statistics. So we are moving off from descriptive statistics to inferential statistics. So I told you earlier, inferential statistics is you look at something in a sample in order to prove something in the larger population. Okay. So important thing to remember is we never prove anything in science. We only falsify the opposite of what we want to prove. So falsifying is easier than actually proving something. So this was the philosophy of scientific inquiry, initially put forward by Karl Popper. You can only show that the opposite is untrue. By showing that the opposite is untrue, you're adding credibility to your own belief. So this is called falsifiability, falsification. That's how science proceeds. So if you believe in something, then you have to state the opposite of it and you have to disprove it. That's the bottom line. So let's say you believe olanzapine is better than placebo. You have to state the opposite of it. What's the opposite of olanzapine is better than placebo? Olanzapine is not better than placebo, or placebo is better than olanzapine. Okay, when you say placebo is better than olanzapine, you're taking a direction there. Okay, that's called one-tailed hypothesis. You're putting a greater than or less than symbol. So that's called a directional statement, and that's called one-tailed hypothesis. Okay. If you make a statement which defies directions, you say that olanzapine is not same as placebo or placebo is not same as olanzapine, you're just putting a not equal to sign. That's called a two-tailed hypothesis. Okay, so this kind of statements where you either say that one is these statements where you propose the opposite of what you want to prove. Those opposite statements are called null hypothesis. Okay. And your own hypothesis, what you actually believe in, that's called alternate hypothesis. This is a bit of a paradox. You won't call your own thing as alternate usually, but here in science, what you want to prove is the alternate hypothesis. What you want to disprove is the null hypothesis. Null hypothesis is something you want to nullify. Okay, in this slide, I'm going to show you some interesting concepts. So let's say this green circle represents the truth, the actual truth. So you want to, the actual truth is, let's say you are trying to find the difference between treatment A and treatment B. And in actual truth is, there is a difference between A and B. The actual truth is, let's say A is greater than B. That's the actual truth, and that's represented by this big circle, green circle. But you cannot study everyone in the big circle. You cannot study the entire universe or the entire population in order to establish if A is greater than B. You're going to take a small sample, and in this sample you're going to see if A is greater than B or not. Okay, so you have a sample and you're going to see if A is greater than B in this sample. Okay, the reality is, yes, A is really greater than B. Okay, and you have a small sample in which you are testing. So I have a 2x2 table where I'm plotting the two outcomes of what you can observe in your sample. In your sample here, you can either reject your hypothesis, you can say A and B are equal, or you can accept your hypothesis, which is A greater than B. Okay, so you have two outcomes. First, you're rejecting your hypothesis. Secondly, you're accepting your hypothesis. Two outcomes. Two outcomes are possible in your own sample. Either A is greater than B or it is not. Okay, so if A is greater than B, that's the outcome shown here. And if A is not greater than B, if A is equal to B, or if B is greater than A, that's the outcome shown here. Okay, so you have two outcomes. Reject, either you reject or you accept your hypothesis. So the universal truth in the green circle is shown here in these two things. In the universal truth could be there is no effect, there's no difference between A and B, or it could be that there is a difference between A and B. Okay, there's a difference or there's no difference. These are the two possibilities in the universe. These are the two possibilities in your own study. Okay, let's see what are the two places where we make an error. So there are two places here, two boxes where we make an error. What are those two boxes? Can you see type 1 error here and type 2 error here? So let's look at type 1 error first. Now type 1 error is a condition where you in your own sample you accept your hypothesis, which means in your sample you are showing A is different from B, but the real effect, the universal truth, is there is no effect. That's the reality. There is no difference between A and B, but somehow in your sample you end up demonstrating a difference between A and B. Now that kind of error is called type 1 error, and in science we really want to keep type 1 error really low, because type 1 error could affect scientific progress. If somebody claims that something is true which is not really true, and that could mislead science for years and decades. So we want to keep type 1 error low. And how low do we want to keep it? 5%. Okay, and this is where we get the p-value. Significance level 5% comes from this. Type 1 error is also called false positive error, because this is a situation where you falsely report a positive result from your study. So this is false positive error. 5% is what we want to keep the probability as. Conventional probability is 5%. Look at the type 2 error. When do we make a type 2 error? An effect is really present. So the reality is A is different from B, but in your own sample you're rejecting it. You're not actually observing the difference between A and B in this situation. So you are making an error of omission. You are omitting what is already there. You are not able to observe it. So this is called type 2 error. Now we are a little less conservative when it comes to type 2 error. We keep it as 20%. We don't go as low as 5%. We keep it as 20%. Okay. So the most common reason why you don't find something that is out there is you're not searching in enough places. Imagine you lost your purse or your wallet. You want to find out where your purse is at home, but you're searching only in your bedroom. You're not searching your office where you kept it. So if you're not searching enough, in other words, if you have small sample, if this orange circle is very small, this orange circle which is your study sample size, if it's very small, then you may make type 2 error. Okay, so remember this, the most common reason for making type 2 error is having a small or weak sample size. Why do we make type 1 error? The most common reason for type 1 error is over enthusiasm. The researcher is very keen to show something. They test something multiple times. If you keep doing something, you will find at least 1 out of 20 times you will find something. Okay, so type 1 error is due to over enthusiasm, multiple testing. Okay, type 2 error is due to weak sample size. So the columns here add up to 100%. Okay, so if you add up the column, these two boxes, it will make 100%. So if this is 5%, what should this box be? 95%. Okay, same way, if this is 20%, what should this box be? 80%. Okay, so let's talk about this box now, the confidence level. Confidence level of a negative study. We often don't say confidence level of negative study as a full term, but this is what you need to keep in mind. When we talk about confidence level, we talk about confidence level of a negative study. So what is happening here? You are rejecting your hypothesis, which means your study is negative. You are not finding any difference between A and B, and in fact there is no difference between A and B. Okay, so what you did is right. And how confident can you be in your negative result? We want to keep that confidence very high, 95%. So this is 5%, this is 95%. Okay, so confidence level is the ability to reject your hypothesis correctly. What about this box here? This is power. Power is usually kept as 80%. If this is 20, this is 80. Okay, what is power? What is happening in the power box? You are showing a difference between A and B, and in fact there is a difference between A and B. In other words, your orange shape here, orange circle or orange oval, ovoid, is representative of the green circle. Okay, in other words, your sample is quite representative of the population. Your sample has the ability to deduct the difference that is coming from the whole population. So power is defined as the ability to find a true effect, ability to find an effect if the effect really exists. Okay, the ability to find an effect if the effect really exists. That's called power, and we want to keep that as 80%. So those are the 4 terms I want you to keep in mind. P-value is given by false positive error, significance level. Power is 1 minus beta. Beta is type 2 error, and 1 minus alpha is confidence level. Okay. Now p-value is the probability of falsely rejecting null hypothesis. Okay, lower the p-value, better it is. Power is the ability to deduct a true difference if it exists, and it depends on sample size. Now how do we interpret p-value? If p-value is 0.01, the risk that the result is false positive, the risk that the result is due to chance, is 1 in 100. Okay, so 0.01 is 1 in 100. 0.05 is 5 in 100. 5 in 100 transfers to 1 in 20. So the most common reason why we inflate type 1 error, why we make type 1 error is multiple testing. You keep testing for something, you will find something even if that shouldn't be there. Okay, so let's say if you keep fishing at the same site, same place in the river bed, you may not have, that place may not be a place with a lot of fishes, and you may not be a good fisherman, but a good angler, but you might find at least one fish if you keep fishing in the same spot for 20 days. Okay, so that doesn't make you a good fisherman or a good angler. The multiple testing produces type 1 error, and weak sample size produces type 2 error. All of these variables are dependent on each other: power, sample size, p-value, effect size, variance. Okay, what do I mean by, you know what power is, what sample size is, and what p-value is? What is effect size? Effect size is an umbrella term to talk about difference between two groups. Whenever you have two groups and you measure the difference between them, you could measure either the difference in terms of subtraction of some values, or you can have a ratio that compares the two groups. Whatever it is, if you have a relative term or a difference term, that is called effect size. So in the past, when we made 2 by 2 tables, we have seen many ways of reporting effect size. Do you remember any of them? Yes, RR, OR, ARR, RRR, all of these are measures of effect size. And when we put people into boxes, that's called categorizing, that is categorical data, putting people into boxes, responder, non-responder, people with EPSC, with no EPSC. So those kind of categorization will give rise to ratios. But if you don't have categorical differences between groups, let's say if you are measuring weight of one group and compare it with weight of other group, you don't have any categorization here. You just have average weight from two groups. Subtract the two averages. That's the measure of effect size. Okay, just subtraction between two groups is also a measure of effect size. ARR, subtraction between two groups, right? And that's a measure of effect size. So whenever you measure effect size, remember the size of the effect could depend on the variability in the population. So if a metric is highly variable, then the large differences you see may not be that meaningful. Okay, because that could be random. Let's say height is quite variable among people. Just because two random group of people have different height doesn't mean they have different genes that are determining their height. For example, that could be a random chance. Okay, so that variance is usually measured using standard deviation or standard error. So you have to take in account, whenever you talk about effect size, you have to standardize the effect size to the variance. This is what we get when we compute something called Cohen's d. Cohen's d is subtraction of average between two groups. So you have group A, group B, take the average of two groups, weight, subtract it. Okay, mean 1 minus mean 2, and then you divide that difference, the subtraction, you divide that subtracted value by pooled standard deviation. You put everybody together, both groups together, find out what the standard deviation is. You will, whenever you have a group of people, whenever you have a central value, mean value, you can also have a standard deviation. So find the standard deviation and divide the average difference between two groups by the standard deviation, and you get Cohen's d. So Cohen's d captures both effect size and variance. So we call Cohen's d, Cohen's d is called standardized mean difference, SMD, standardized mean difference. Standardization takes care of variance, mean difference takes care of the effect size. So power calculation, well, it's a bit of a misnomer. We don't calculate power. Power is kept as 80%. This is sample size calculation. So you want to calculate sample size. To achieve 80% power with a p-value of 0.05, what is the sample size required in order to demonstrate a particular effect size given the specific variance of your observation? So all of these are related to each other. When we do power calculation, we put all of them in an equation and we find out what the sample size could be. Let's do some questions now. In a study evaluating the degree of recovery achieved following an episode of psychotic depression when using pharmacotherapy, the study group wants to increase the power of the study after initial piloting of the protocol. Which of the following can be useful? Increasing the heterogeneity of the sample, using self-rated questionnaires as outcome measures, comparing two active treatments, comparing an active treatment versus placebo, reducing the number of participants. So how can you increase power? You can increase power by increasing the effect size. The effect size of the thing that you're looking for, if it is large, then you will be able to find it easily. The ability to deduct what you're looking for is easier, is higher if what you're looking for is a larger object, if it has larger effect size. So in the situation given here, what will increase the effect size? Comparing two active treatments, no, both are active, so the difference between them will be low. But if you compare active versus placebo, the difference would be more pronounced. So in this case, you will have better power. D is the right answer. Okay, the next question. With respect to inferential statistics, which of the following is not correct? The probability of a type 1 error is related to alpha. The probability of type 2 error depends on the sample size. The power of a test depends on the sample size. The p-value indicates the probability of null hypothesis being true. Two-tailed hypothesis may have a different significance levels than one-tailed hypothesis for the same research question. So they're asking for a statement that is not correct. Okay, probability of type 1 error related to alpha, that's correct, because alpha is confidence level and type 1 error is related to it. It's the complement of it. So alpha is, if you keep alpha as 5%, p-value is 5%, and then confidence level is 95%. So these are related to each other. Okay, the probability of type 2 error depends on sample size, that's true as well. Power of a test depends on sample size, yes, we know that. They are all interrelated, power, p-value, sample size, and standardized effect size. P-value indicates the probability of null hypothesis being true. No, p-value indicates the probability of falsely rejecting the null hypothesis or falsely making a acceptance of the alternate hypothesis. Okay, so this is probability of false rejection of null hypothesis. So D is not correct. D is false. In large trials where multiple resources are used, investigating teams may use the final dataset to answer various different questions they might have. Such multiple testing leads to type 1, type 2, selection bias, confounding error, type 3 error. So we know that multiple testing inflates type 1 error. A. From the following options, choose the correct pair of statistical measure and value of no difference with respect to confidence intervals. Relative risk 0, odds ratio infinity, absolute risk reduction 0, relative risk reduction 1, number needed to treat 1. So for the moment, remember the answer is C, absolute risk reduction 0 is the right answer. After the next question, I will show you a slide with a table where I will show you all of the effect size variables and the value of no difference for each of them. Okay, and when we go through confidence intervals, you will understand this in much more detail. So the answer for this is C. When you see the next question, you will know why. In a study exploring presence of suicidal ideation in those psychiatric patients who are currently smoking compared to non-smokers, the following was found. Odds ratio is 2, 95% confidence interval is 1.48 to 2.7, p-value is less than 0.0001. Which of the following can be inferred from the above? First of all, A, confidence interval embraces value of no difference. Is that correct? This is an odds ratio. For odds ratio, the value of no difference is 1, because whenever a ratio is 1, that means both the numerator and denominator indicate the same value, which means the two groups you are comparing have the same risk value. So odds ratio, if the confidence interval contains 1, that becomes insignificant. 1.48 to 2.7, do you have 1 in between? From 1.48 to 2.7, you don't. So this is not correct. Confidence level embraces value of no difference is not correct. Confidence interval does not show the size of the effect. Now confidence interval always shows the size of the effect. Here the effect size varies between 1.48 to 2.7. Okay, this is why we prefer confidence intervals to p-values. P-values only show the significance of a test. They don't show the size of the effect. In a confidence interval, you can also see the significant level, whether it's significant or not. You can look at it by looking at the range and whether the value of no significance is contained within it or not. At the same time, we can also know the effect size. So A is wrong, B is wrong. Degree of bias can be estimated from a reported confidence interval. Now looking at confidence interval range, you can say how precise the result is. If the range is narrow, the result is very precise. But you cannot say whether there has been bias in the conduct of the study. So for example, if there has been attrition bias, recall bias, those things you cannot know by looking at the numbers of the confidence interval. So C is wrong as well. D, the risk that given odds ratio 2 is a chance observation is 5%. So the risk that given odds ratio 2 is a chance observation is given by the p-value. How much is the p-value? It's less than 0.001 in this case, 0.001 in this case. So it is less than 1 in 10,000. It's not 5%. It's less than 1 in 10,000. So this is really a small p-value. So D is also wrong. E, none of the above are possible. That's the correct answer. None of the above inferences are possible. Let's look at the confidence intervals in a little bit more detail. So whenever they give you a confidence interval in your exam, or when you read a journal article, if you see confidence intervals being reported, there are a few things you have to keep in mind in order to interpret the confidence interval. In fact, you need three things to remember. Number one, look at the summary measure. So this is called the summary measure. In this case, it's OR. The example on the bottom, it's ARR. So these are the summary measures. Summary measure is any measure of effect size. It could be RR, OR, ARR, NNT. Any of these could be summary measures. And the value of the summary measure is called point estimate. Why is it called an estimate? It's estimate because this is what you note from your sample. This is what you observe from your sample. You estimate from your sample a value, and you think that value could represent the universal truth in the larger population. Okay, so this is the estimate, point estimate, and it's 2.4 in this case for OR. Okay, and you present confidence intervals to show what is the likely range in which this summary measure could lie if you do 100 sampling. If you do 100 samples from the same population, 100 samples of the same size, then 95% of time, 95 times out of 100, your summary measure is likely to have a point estimate between 1.7 and 3.4. So that's how you interpret confidence levels. So in other words, this range tells you where the likely truth is going to lie. Okay, it's going to lie somewhere between 1.7 and 3.4. Remember, the point estimate will always be contained within these two values. So when you move from 1.7 to 3.4, if you go stepwise, 1.7, 1.8, 1.9, so on and so forth, at some point you will encounter 2.4, summary, the point estimate. Okay, so this is a plausible observation. If you have an observation where they give you a point estimate that is not contained within the range of the confidence intervals, then that's an error. There's some kind of statistical error, mathematical error somebody has done. You should always have the point estimate contained within the range of the confidence intervals. Okay, so what are the three things I want you to remember whenever you interpret confidence intervals? Number one, look at the nature of the summary measure. Is a summary measure a ratio or is it a subtraction? If the summary measure is a ratio, then you have to keep in mind the value 1. 1 is the value of no difference for ratio. For a subtraction like ARR, 0 is the value of no difference. Okay, so for OR it's 1, for ARR it's 0. What about other metrics? So we have OR 1, value of no difference, RR also ratio, so 1 is the value of no difference, ARR is a reduction, so 0 is the value of no difference, RRR is also a reduction, so 0 is the value of no difference. NNT, for NNT is a reduction, but it's an inverse of a reduction. It's 1 by ARR. Okay, so for NNT the value of no difference is 1 by 0. What is 1 by 0? Infinity. So infinity is the value of no difference for NNT. So keep those numbers in mind, whether it's a ratio or it's a reduction or it's NNT. Based on that, you will be using 1 or 0 or infinity. Okay, so most commonly you will use either 1 or 0. So for odds ratio, keep value 1 in mind. For ARR, keep value 0 in mind. The next question you have to ask, so that's the first thing to remember. What is the nature of summary measure? So what value to keep in mind is reference value. For ratio, it's 1. So keep 1 in mind. Next question, check the lower limit of the confidence interval. Is this greater than 1? Yes, it is. If it is greater than 1, because 1 is the reference here. Okay, if it's greater than 1, this should also be greater than 1. Is it greater than 1 as well? Yes. So 1.7 is greater than 1. 3.4 is also greater than 1. So this odds ratio is a significant result. 2.4 reported here is a significant result. So even without looking at the p-value, just by looking at the confidence intervals, you can say if this is significant or not. Okay, so 1.7 to 3.4, both values are greater than 1. It's significant. Look at this one here, ARR. Is this greater than 0? Here now we are looking at 0 because 0 is the reference value for reductions. Okay, so 0, is it greater than 0? No, it's not. In that case, this should also be less than 0. This is less than 0, so this should also be less than 0. Only then you can call this as a significant result. Let's see. Is this less than 0? 0.51? No. 0.51 is greater than 0. Minus 0.7 is less than 0. Okay, so these are not in harmony. These are not consistent. The lower limit and upper limit are not consistently on the same side of 0. Okay, So now we call this as insignificant result. So this is insignificant, this is significant. Okay, so that's how we interpret confidence intervals. So the answer for MCQ 15 is last one. None of the above inferences are possible because all of these are wrong. Let's look at odds and probabilities now. What is odds? Whenever you bet on a horse or when you gamble, you use odds. What is the odds? Odds is the chance of something happening. So your lucky number winning the race compared to the chance of the second horse or the third horse winning a race. Okay, so odds is chance of some event happening in relation to other event happening. Odds is expressed whenever you have binary outcomes. Odds is used when you have a binary outcome. Okay, probability is the chance of some event happening in relation to all other events happening. So the denominator for probability would include every possibility, every other event. Okay, so denominator is larger for probability, it's smaller for odds. Can you change from probability to odds mathematically? Yes, you have a formula. Probability is equal to odds k divided by 1 plus odds. So odds by 1 plus odds gives you probability. If you have probability, you can calculate odds by using the alternate formula. Odds is equal to probability by 1 minus probability. Okay, so just take the probability value and divide that by 1 minus probability value. You get odds. Now we have a couple of questions. In an acute admission ward, 25 patients are admitted. There are 10 patients with psychosis and 15 with neurosis. If one randomly selects a patient, the odds of him or her being psychotic is 10 by 25, 15 by 25, 10 by 15, 150 by 25. Not enough information. So you have 10 psychotic patient, 15 neurotic patient. Okay, 10 psychosis, 15 neurosis. So odds will be simply 10 by 15. So as simple as that. The odds is C, 10 by 15. In an acute admission ward, 25 patients are admitted. If the odds of a randomly selected patient being psychotic is 2 by 3, then the probability of finding a psychotic patient from the sample is, so they are given you odds, find out the probability. You use the formula. Odds is 2 by 3, probability is equal to odds by 1 plus odds. 2 by 3 divided by 1 plus 2 by 3. Now you got to be careful whenever you add a whole number 1 to a fraction 2 by 3. So when you do that, you take the denominator of the fraction, multiply the whole number. 3 into 1 is 3, and then 3 plus 2 is 5. So 5 divided by 3. So this bracket, the value in this brackets become 5 by 3. 2 by 3 by 5 by 3 is 2 by 5 because you cancel both the 1 by 3's and you get 2 by 5 as the answer. So the answer for this is 2 by 5. And another easy way of doing this is, you know, the probability has larger denominator, correct? So the odds is given as 2 by 3. Probability should have larger number in the denominator. How large would it be? It will be larger by the factor of the numerator. So just take the numerator, add it to the denominator. 2 is added to 3 becomes 5. So 2 by 5. Keep the numerator as the same now. 2 by 5 is the answer for probability. Okay, so far we have seen hypothesis testing, and I have explained to you what is a type 1 and what is a type 2 error. We've looked at p-value, we've looked at power calculation, sample size calculation. We also know something about confidence intervals, and we looked at odds and probability formulas.